So this was, for example, if I had a marker, oh, you might work. Okay, let's see. So we did problem like the school has outlawed the board cleaner, you know, the spray. Yeah, I brought my own spray once. Actually, I have it in my office, but I asked for a board cleaner and they brought more erasers, and I'm like, no. I'm like, yeah, that's it, dude. Because I could. Huh? That's very nice, because I could kill you with the chemicals, apparently. But I mean, if I smell these enough, I'll get high. I don't know. So we did a problem like 2 cubed times, 3 squared. What number is that, by the way? $72. So that's the number 72. So it's prime factored already. Does anyone remember how to get the shortcut to figure out how long the list of factors would be? Starting with 1, 2, 3. How long would that list be?
Don't you just add the 1 to the exponent, like each exponent?
Sure.
And then you do the 4 times.
Times, good.
Yeah. Yeah, and then that's.
What kind of number is 2? What kind of number is 3? They're both prime. I like it. So in the example I gave you, I didn't tell you what P and Q are, but I did tell you have how many of each? So what's the power on each one? So then you do the exact same thing. It doesn't matter what they are. What matters is that they're prime. No matter what they are. So again, if I had 17 to the 4th power, times 23 to the 2nd power. Are 17 and 23 both prime? Hell yeah. So then how many factors would, whatever that number is, I don't know what that number is, right? 17 to the 4th, you could all do it in your calculator, gets this big ass number. How long of a list of factors would that number have? The process in math doesn't care what the numbers are. Yeah, because you would do 4 plus 1 times 2 plus 1, 5 times 3. There would be 15 total factors, right? It does not matter what the prime numbers are. I really want you to get this, right? I don't care if it's 2 and 3, 17. As long as they're prime and you take their powers and add 1, we talked about why that makes sense. Can somebody remember why we add 1? Can anyone remember why we add 1? Yeah.
Because we can also not have that.
Yeah, I could have 0 17s and 2 23s, and that would be a factor, correct? So I could have 0 17s, 1 17, 2 17s, 3 17s, 4 17s. So I can have 5 combinations, including a certain number of 17s. Are you guys, remember, that's exactly how we derived this idea. So over there, I'm just saying, all right, I'm not going to tell you P and Q are, but you know you got 1 of each, right? So apply the process to this. How many factors could this have then? Yeah, 1 plus 1 times 1 plus 1, 2 times 4. You can have 4. So no matter what you picked for the P and the Q, if they're prime, you're golden. Now, let me ask you this. Why do you have to be a little careful with something like, what do you got, Jeff? Like something like this. You could do it, buddy. Write a number. There, look at that number. All right. Why can't you just do 2 plus 1 times 3 plus 1? Yay. Yeah.
Because 9 and 15 have other factors.
They're not prime numbers. It hasn't been broken all the way down. So there were some problems in the homework. I think like one of them was 12 to the 4th. So you had to break that down so you can actually see what are the exponents on the prime parts of this. They have to be prime, and then you can do the shortcut. And it's kind of nice to know how long the damn list is, because the bigger the number gets, the easier it is to forget somebody. So if you know ahead of time it's supposed to have 14 things in it, and you only get 12, and you know, okay, I missed 2. Let me go see what the hell that is. Okay, maybe. And again, just to really make this more concrete, this is 72, correct? So if I start listing the factors in 72, well, I can't remember if this is in the book or not, if I just told you this. How do you figure out the turning point, and what the hell does that mean again? Square root. So that's where you know you can just stop really thinking and just start pairing it up with earlier numbers. Does anyone know what the square root of 72 is roughly?
A little over 8.
Yeah, it's between 64 and 81, so it's between 8 and 9. So the turning point will be around 8. So let's see. What else goes into 72? 4, 6,
9.
and now I start, 9. Well, you forgot
Oh,
8. And now that's the turning point. I really want you with me. Square root of 72 is a little more than 8, so the turning point should be around 8. What do I mean by turning point? And again, that's my own words for that. It means now I can just start pairing it up. I don't have to start. I can just stop really thinking and just go 8 times 9, 6 times 12, 4 times, become 12. 4 times what? 18. 3 times, now watch this real quick. 4 goes into 36, how much? 4 goes into 36, how much? 9. Isn't this twice as big as 36? So 4 goes into this twice 9, 18. Right? Where are we at? I forgot. 3, all right. 3 goes into 36 12 times. This is double, so double 12 is 24. Cool. Where am I at? So that's 3 times 24, 2 times, that's easy. 36, and then 1 times 72. How big is this? Is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 4 times 3, 12. Okay, that's the concrete idea behind what we're doing here. Okay, maybe. Generally good to know. It will not help you buy lettuce. One semester, I will never forget, this kid in the front was like, how's it going to help me buy lettuce? I'm like, oh my God. Does everything supposed to help you buy? Don't take history class, because it won't help you buy lettuce. Anyway, sorry. I'll never forget that. I could write a book. All right, so that's number 1 on the practice test. So it's wide open to homework stuff, quiz stuff, practice test stuff. Yeah.
Can you do fractions multiplying with the box, like shading the box?
Oh yeah. So like if you had to do, I don't know, 2/5 times 3/4. Does that sound all right? So then, how would you do 3/4? You would just cut that up into 4 parts. So cut it 3 times, 1, 2, 3, and then shade 3/4. That's incredible, Jeff. You can do it, buddy. All right. And then next to that, and again, this is built on the old idea of like 3 times 5 is. Good job, Jeff. And then so 3 times 5 is 15 because you can count them up. Here, the shading is where the fractional part comes in. So 2/5, I kind of just ignore what's here already. And on top of that, I put 1, 2, 3, 4 cuts, so I get 5 pieces. And then I shade in 2 of those, right? So that would be here, here. So then how many are double shaded? How many are double shaded? 6. And what does each box represent? Yeah, 1/20th, because you got 20 parts, right? Cut it into 20 brownies. And of course that reduces to be 3/10. Oh, poor little dude. Now, if you did that by hand, if you actually just did the computation, what would you do as you do the computation? What would happen? First thing, if you just do this, what's the first thing you should do? Two goes into 4. 1 times 3, 5 times 2, 3/10. Right? So it's a cool little visual, right? And you might have seen it sometime in your life, but we very quickly forget about it because you don't spend a ton of time doing this. You're just developing the idea of why does it make sense that we just multiply 5 times 4? Because that represents cuts and then more cuts on top of that. So you're cutting them down into smaller and smaller parts. So you get more parts out of one whole. Yeah?
Is it the same idea as number 5
On the practice test? Oh, sort of, but not really. I mean, what's the one thing you gotta be careful about number 5 on the practice test? It's pretty, hopefully obvious.
The last piece isn't cut.
Yeah, the piece at the top isn't cut. So you can't count that as one piece, obviously. But you can understand, we've seen this, where a student could just think of it in terms of pieces instead of equally sized pieces, right? Okay, and that's sort of a important thing. There's a problem in the book that's really interesting. It does this. Shit, let me see if I remember what it does. Yeah, it does this. Anyway, does that look familiar to anybody? That'll be trippy. And that's a good one to give students after you've had a decent discussion about it's got to be equally sized pieces and so forth. Equally sized does not mean same shape. Do you agree with me? Sort of, not really. Isn't this piece, if I just do cut, that would be cutting it in half, correct? That piece, that box, that would be cutting it in half. If I have this box, it's supposed to be the same size as that box. If I do this, isn't that cutting it in half? All right, so this is exactly the same as this or this. They're all the same. They're all the same amount. They're all the same percentage of that original area. Do you see that? And of course, you wouldn't want to use the word percentage when you're first talking about fractions because they don't understand what the hell percentage is yet, but you guys know what percentage means. Maybe? Okay. No, yes? You guys remember that problem? So it's really easy to understand. In fact, part of you would want a student to have some trouble with that, to go, I can't do that. They're not, because that means they understand the idea they got to be equally sized. And then you show them, okay, now we can go a little further and realize both of those represent half of the respective little boxes, right? So overall, each little piece means 1/4 of the whole thing. Okay. Maybe. So for example, how could I cut this in half? I could either just chop it here. That's cut in half now, right? It's incredible. How else can I cut this in half? Like that. Right? How else can I cut this in half? Like that, right? So each of those represents half of the same original size box. So they're all equivalent to each other, each part. Okay. I like it. So you want to be careful when you're teaching students. You want to start with all the same shapes. So visually, it's really easy to catch on. And then you move on to the shape doesn't matter. Just the amount of the original thing matters. Right? Then you can move on to that kind of problem over there. Okay. Maybe. Is that all right? I do tend to go a little further with the problem than I need to, but. What else is freaky on there? is anything. Yes.
Number 6 on the practice list.
Yeah. So that would be, once you get past like the visual of, what fractional part of this is shaded, you would say 1 out of 4, right? It's 1 part out of 4 total. So it's part divided by whole. So then you can kind of expand and say, anytime you have a part of something and the whole thing, you can make that ratio, and that's a fractional part of that thing. So it doesn't have to be just visual. So in this problem, it says the monthly income is $9,600, and $1,200 of that is spent on food. By the way, do you guys remember, again, this is a little ahead of where we are currently, but just, do you remember problems like, what percent of 17 is 38? Stuff like that, right? Of and it is over of. Does anyone remember what I'm talking about? Is over of. There's so many different ways to teach that. That's sort of like what this is talking about. It's fractions are always, or not always, fractions are most of the time part divided by whole. So we say this in English the exact way you would write this in Mathish. Out of $9,600, how much do they spend on food? 1,200. So they spend 1,200 out of 9,600. Isn't that a fraction that I just said? What fraction did I just say? 1,200 out of 9,600. And then you just reduce that, right? Okay, maybe. Okay. Anything else? Do you have the practice test? Everybody's got a practice test, right?
I
Okay.
have it in my car.
You want a copy?
Yeah. Thank you.
Sure.
Can you explain like the proof of like why you can't add straight across, but you can multiply straight across?
Oh, all right. So, okay. The way I can talk to you guys about it is different than the way you would talk to somebody just learning this. Because I could talk to you about like terms, algebra ideas, right? So when I'm teaching, well, I can't say present tense. When I used to teach Math 88 here, right, which is equivalent to like elementary algebra, I'd be able to say you can't add 2 fractions unless they're like terms, the same way you can't add x and y, but you can add x and x, right? So a student's not going to understand that. I mean, if they're young enough to just be learning fractions, they're not going to be able to understand that. So there, what have you done as you've built up to adding fractions? So one of the first methods we use when we're teaching an idea to a very young person is visual, right? You always start with the visual. In fact, not just visual, but the, what's the word? Kinesthetic? You can actually, kinesiology, yeah, kinesthetic. Something you can actually hold. That's why we have all those manipulatives, right? They want to be able to hold stuff and actually feel them and put them over there and move them around. So what have you done to get a student to understand like 1/4 plus 2/4? What do you think? What kind of problem have you done? Maybe something like was on the last quiz. I can't remember now. What? Give me a problem. Give me a visual that you would give a student to think about this problem.
You could do what you did over there with the 1/4.
Yeah. So here's 1/4, and then how will you represent 2/4? Yeah. So you could. So anybody in here ever played Trivial Pursuit? It's probably Trivial. We used to joke. Trivial Pursuit is the game you wait until you can say I don't know, and then somebody else. So you could have little parts that you could actually pick this up and put it in there, and pick this up and put it in there if you have something you manipulate. Does that make sense? Because visually, what you're going to do is you're going to take this and this, and you're just going to throw them in here. Why does that make sense to them? Because before you're doing this, holy crap. I almost took my eye out. Get up there. Stop. You will have done stuff like this, right? 3 plus 4. And you actually physically can put them together. They can move the stuff over. They can, right? Or visually, you can just draw 3 more. You can just take those 3 circles and put them in there. So they're used to this idea of moving stuff into something else, right? So if I take these 2, of course, and I move it into that one, you're not going to believe this, guys, but I get 3/4. That's crazy. Now, then you start to say, okay, what about 1/4 plus 1/2? The visual will look a little different now, right? We know it's the same thing. But how would they, so the 1/4, they would do this. They're cool with that. The 1/2, they just have to cut it once, and they can maybe cut it a different way, but it would be this, right? So they can see visually that they can't pick this up and fit it in to one spot there, correct? So there's a few different ways you can say that. You can't fit that into that spot. You have to actually fit it into 2 of these spots. And what does that relate to? The fact that this is actually 2/4. Or what can you do with that picture once they've drawn it? You can cut it in half again. And they'll very quickly, and then you say, okay, do you agree with me that the same amount shaded? Yes. So that represents the same number. Yes. But how would you say this number now? 2/4, right? So while you're teaching them how to find LCD, you're actually showing them why you need it, right? Before I did this, it doesn't make any physical sense to try to shove that in somewhere. So I don't have 2 somethings. I can't, because this is going to take up more space. Does that make sense? So that's a visual way to explain that. Another way you can explain it, you can do like terms with them to some degree. So for example, if I have 7 triangles plus 2 triangles, that's 9 triangles. But if I have 7 triangles plus 2 circles, is that 9 somethings? No. It's not 9 triangle circles. That doesn't make any sense. Okay. So you can discuss like terms, just not using algebra, not using variables, using shapes, using something else. Okay, maybe. I don't know if that is one route you can go, is the visual. Because this is nice, because you're going to do this anyway. And then you can kind of point back to this and say, now you see why I need these to be the same. It's the same thing as making sure you have the same number of cuts. That's all LCD really is. Is that better? Is that all right? Okay. All right. Yeah, number 9, for example, we talked about directly, right? So expect this, real quick. I saw your hand back there. Expect this. I'm going to give you a problem. I'm going to say, and I've already done this to you, but I'm going to say, here's what a student did, right? Can you figure out? So I'm going to say, well, is it correct? Almost certainly it's not, right? Except we saw that one problem last time where one was wrong and the other one was right. So you got to be careful. Don't just assume it's not right, but, good bet. And then you got to figure out what the hell the student did. And I keep telling you guys, that is the hardest thing sometimes. To figure out, not just, it's really easy to tell something's wrong. The more important part of your job is what went wrong, right? If you can figure out what went wrong, and how to say that phrase, you could figure out how to help the student understand better. But trust me, I've been teaching for, holy shit, 25 years. Quarter of a century. Damn. Started teaching when I was 26. I've almost been teaching half my life. Anyway, sorry, Jeff's having a lot of realization. And I've seen crazy ass logic, and I figured out what they were thinking, and that is crazy important. Because especially when teaching really younger students, you want to show them, yes, you were thinking correctly about this part, but you didn't think about this. And you need to help them connect with the way they're thinking, with the way they're supposed to be thinking. And if the teachers that don't put any time into that are the ones that turn students off to math so quick, because then they feel like, I was just completely wrong. I wasn't thinking right at all. Screw this math shit, right? Okay, maybe. All right, sorry. Yeah, good. 19? Oh, okay. Yeah, 19B is a little bit of a beast, but so let's see, 19A. Where'd it go? 1.46. So I want you to add these using the fractional approach. So very obviously, your first step is to write them as fractions. That's crazy. So there's a few different ways you can write this one. I'll write it the first way I hear. 13 and, okay, so there's 13 and 467 thousandths. I love it. And just to remind you guys, 1, 2, 3 decimal places, 1, 2, 3 zeros. It's got to be that way because it's our base 10 number system. It should be easy. So what's this going to be? Yeah, 1 and 46 over 100. Now, you got to understand this, and I think this is part of the reason why some parents are like, what the hell are you showing my students? This is not making the problem easier. Do you guys agree with me? This is not making the problem easier, but it is when you have somebody who's never added decimals before, but they have added fractions before, right? That's what people fail to understand. They think the student should know everything they know, and why are we making this hard? No, I'm trying to base it on something I've already done, and then show them a shortcut, and that's what we actually do when we line the decimals up, right? So are these like terms? Are these something I can add together? No. So what I have to do here, yeah, multiply by 10. All right, now it's very straightforward, right? And it might be hard for us to understand this, but a student who is at this stage of their development would feel much more comfortable with the fractions than they do with the decimals. So what do I get? 14 and 927 thousandth, which is what is a decimal? 927. Okay, kick ass. And you know, it's not, you can start to see, we all know that is the barest step away from what you actually do with the decimals. But again, you've got to connect what they've already done with what they're about to do. You got to make those connections. Is that right? Part B, I'll figure something out. Well, okay. Part B, why is that rougher? It's not the division necessarily, but so again, we can, this time I would highly recommend, what's the other way I could have done this, by the way? What's the other way I could write this? One way I can write this, what place is that in? So the whole thing's in the tenths place. So I could have written this, the 13 could have just went right up there. In fact, what's 1,000 times 13? 13,000 plus 467 is 13,467 over 1,000. So I could just put the whole damn thing up top. Whatever the last digit's in, that's the place for the whole damn thing. Okay, I'll lock it. Divided by, what's this do? 833 over 100, kick ass. And of course, we've talked about this quite a bit. What do you do when you divide fractions? No? Oh, by the way, the earlier question, I forgot the second half of it. why do I have to get LCD when I'm adding, subtracting fractions, but not when I'm multiplying? And you actually, again, you have that visual. We did that earlier problem with the 3/4 and 2/5, I think it was. Remember we did that visual? So that's a beautiful visual that kind of goes into why you multiply straight across, because visually that's exactly what you end up doing. Later you can start to reinforce the idea that multiplication is nowhere near as restrictive as addition, subtraction. Right? What do I mean by that? Like, I've done this several times. You can't add x and x squared. X plus x squared is x plus x squared. But you can do x times x squared. Correct? So multiplication, division is always less restrictive than addition, subtraction. So here, what do? Reciprocal times 100 over 833. And then, of course, what immediately reduces? Yeah. So I get 5643 0 divided by 833, and then, I mean, that's kind of gross. I didn't really intend. I'll try to make a better problem. So you would have to long divide that anyway, so you'd have to do decimals anyway, so that's kind of silly. So if I give you a problem like this on the test, what should I do here? I should find two numbers that would reduce well, right? Yeah.
Where did you get 5643 from?
I don't know. Oh, here.
34 is fine.
Is it 34? Is it? Oh. Oh, I see. Okay. Thanks, Ryan. It's all the same stuff. All right. I don't think that helps me with dividing. By the way, is the bottom divisible by 3?
No.
What are you checking? What's the rule for 3? Yeah, if you add them up. So you can pretty much see really quickly 3 and 3 are good, but 8's not good. So you don't even have to add them up, to be honest. That has to be a multiple of 3 because the other two are also normal. But if you add them up, you get 14, right? It's not a multiple of 3, so I know 3 won't go in. 5 won't go in. All right, it's not even, so 2 doesn't go in. Do you see what I'm saying? So trying to figure out if this reduces, it's looking less and less and less likely, or at least it's not some easy prime number. So if you give you a problem like this on the test, I want this to be a problem that you can do all the way through without a calculator, obviously. That's the point of it, right? So if I gave you two that actually reduced nicely, that would be good, right? So I'd probably do that. Okay. Is that all right for those two? Okay. How would I do this with, how would I long divide those? What's really funny is the answer is up there already, how you would long divide it. But how do I long divide decimals? What do I do? So if I just write this problem in long division form. No, Jeff, you can do it, buddy. What is it that we have to do? Yeah, this has to move over once, twice, so therefore this has to move over once, twice, 0. Isn't that exactly what this says? So again, this is actually an explanation for the shortcut of what to do with long division. You guys see that? So it's desperately important. I've said this before. I've seen way too many teachers teach the shortcut without explaining what it's based off of, right? Which is horrendous. It's the worst thing in the world. Because then students sort of start to learn, oh, I don't need to question, I just need to memorize this shit. It's not based on anything, it's just stuff we made up. No, my God, it's all based on something. Okay. Natalie, you here? Hey. Let me ask you this question real quick while there's no questions being asked. What's due this Thursday? All right, quiz and test corrections. Homework up through 7-2. I like it. What about homework corrections? Final exam, 11. So basically everything's due the day of the next test except for homework corrections. I love it. Nice thing is the day before the last class before Thanksgiving, it's always nice to have a test for students because then you basically have nothing to worry about over that week except for maybe catching up on homework. Right? Teacher, hey, we get to grade shit. Yeah.
Oh, no.
Okay. Solidarity. I like it. Anything else? Any other questions? Or do you want me to ask myself questions? I could do that. Number 12 sometimes gives people trouble, but how'd that go for you guys? Number 12, did you try that one out in the practice test? No? Do you see how to do it?
Can you make it improper?
Yeah.
And then
You gotta make it improper. I love it. Yeah. So if it's a mixed number, it doesn't make any sense because I'm supposed to flip the fraction, but a mixed number, I can't just say the fraction because there's a whole number and a fraction part. So I gotta make it one fraction and then I could flip the fraction. Kick ass. What about number 15? I'm getting, so let me ask you this. What's the purpose of estimation? Let me bring that in a little bit. Well, let me start with that. What's the purpose of estimation?
Answer close to what you're trying to find.
That's right. So if you're doing some computational problem, you can kind of tell, does my answer that I got make sense? So if I estimate that it's supposed to be 240 and I got 24.3, some kind of decimal problem happened, right? Now, with that in mind, estimation, I'm supposed to change the numbers into numbers I can do in my head, basically. Estimation is supposed to take a problem that requires some algorithm and try to make it into one I could do in my head entirely. So I get too many people doing stuff like, so this one says estimate 17.6 divided by 6.367. And I'll get somebody say, okay, that's roughly 17 divided by 6.37, and then they'll give me a number. I don't know about you. I could do this in my head to a degree. I don't want to, right? So I really want to focus on this problem for a second because what's the right way to do this problem? What's a better way to do this problem?
Rounding the numbers to the nearest whole.
You could do that. If you did that, what would you estimate this to be?
18 over 6.
Oh, okay, not the I'll say nearest whole, I got you. Not nearest 0, not nearest 10, but nearest whole. I like it. So this would be 18 over 6, which is 3, right? Can anyone tell me, is that estimate too high or too low? And why? No, we know exactly if it's too high or too low. And you're all like, maybe you do, dude. If I make the numerator bigger in a division problem, does the answer get bigger or smaller? If I just change the top and make it bigger, does the answer get bigger or smaller? Bigger. So, like for example, what's 20 divided by 5? 4. What's 30 divided by 5? 6. Okay. So if I make the top bigger, obviously the answer gets bigger. Does that make sense? Because I'm starting with a bigger number, so of course when I divide by the same number, I'm going to get more, right? If I make the bottom smaller, so again, let's do this. What's 20 divided by 5? Holy shit. What's 20 divided by 4? I made the bottom smaller. What's 20 divided by 4? The answer got bigger, correct? So if I divide by less, the answer becomes bigger. So everybody with, didn't we just do both of those things? We made the top bigger, that makes the result bigger. We made the bottom smaller, that makes the result bigger. So is this too high or too low? Way too high. I mean, not way too high, but that's too high, correct? Too damn high. Damn. Okay. Can somebody real quick put that in your calculator, if you have it right there?
2.76.
Yeah. Less than that. We're not that far off, again, because we didn't really move it that much. But it definitely is, I know for sure that's more than it should be. And I think there's at least one problem in the homework that's kind of like, in this situation, should we estimate too high or estimate too low? So if I'm trying to figure out how many chairs I need for some event, should I estimate too high or estimate too low? Too high, of course, right? It's not going to be good PR if there's no chair. Okay. Yes? 10. Oh, yeah, cool. This is one, I thought for sure somebody would ask that like immediately. So showing off my creative chops, Mr. Last Name left 1/2 of his estate to his wife and blah, blah, blah. Did anyone try that problem? Do you think you got it right, maybe? Or how comfortable are you?
Well, I made all the fractions into common denominators.
So let me ask you this first. Tell me all the fractions you were working with.
1/2.
Okay, so 1/2 of his estate went to his wife. Sounds like a good idea. Of course, it's up to each individual.
1/9 and 1/24.
Be careful, go back. 1/9 went to
3 children.
each of his 3 children. So is that 1/9? 3/9, right? So I'm working with 1/2, I'm working with 3/9. What else we got? Yeah, each of his 3 grandchildren, so that's 3/24. And then the remaining 18,000. Okay, there are a few different ways to do this. I did it a specific way on the test. It just was the practice test. The first way that came to my mind. So I don't know. What you could do this using algebra. What was the total value of his estate? Do we know? In fact, that's the whole point, right? So what are you going to call it? X. X is the value of his estate. Some monetary value, correct? So how much money did his wife get? 1/2 of X, kick ass. Not 1/2. She didn't get 1 50-cent piece. She got 1/2 of the estate, plus 3/9 of the estate, plus 3/24 of the estate, correct? What else do I have to add to that to make it become X? 18,000, that's what's left, correct? So if I add 18,000 to this, that becomes the full amount. Does that make, do you see that? By the way, this is not the way I did it, but this is a way you can do it. And then you do algebra to it, right? So like you said, whoever is talking to you, you got all the denominators the same, right? And blah, 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 blah. Of course, hopefully you would first reduce these. Is that cool? Okay. You guys semi with me? Did anyone try this a different way, or did anybody else try this? Let me ask that first. Did anybody else try anything on this problem? Or were you, okay. Do you understand this way to do it? All right, is anybody curious about the way I did it? I like to understand it. Yes, we are, Jeff, just tell us if we're quiet. So what I did was I added up all these. Whatever they are, whatever's left compared to 1 must be what 18,000 represents. 18,000 is the last fractional part of the estate. So how do I figure out what 18,000 is in terms of the fractional part, I add these up and subtract it from 1. So if I do that, I'll get 1/2 plus 1/3 plus 1/8. What's the LCD there? 24, I think I heard. 12 plus 8 plus 3, 23 24ths. So 18,000 must be 1/24 the estate. You guys semi with me? Does that make sense? This much is 23 24th of the estate. So this must be 1/24 of the estate. So then how do I figure out how much the estate's worth? I just multiply by 24. 18,000 times 24. As I say this, I'm like, did I multiply that right? Let me see. No, that's hilarious. Okay, I'll show you what I did wrong. What I did wrong, for some reason, I just left out the 2. So right here, what should I do? I don't know, is anybody completely not with me? Do y'all understand that the amount of money I've given out, that this Mr. Last Name gave out, is 23 24ths of the total amount of money they had. So the 18,000 must be the 1/24 that would have been left over. So if I just multiply 18,000 by 24, I'll see what the total amount must have been. If you want to see an algebraic thing I'm doing, it's just this. Multiply both sides by 24, you get the answer. What Jeff did was he multiplied by 4, and I remember thinking, that seems small, but okay. So what is 24 times 18? 432,000, okay. So the total estate must have been that. And how do you check your work? Well, you take half of that, you take 1/3 of that, you take 1/8 of that, add them up and see if you got 18,000 left over at the end. All right, so you can actually check your answer. Okay.
How do we solve it that way?
Oh, this way? Okay, sorry. Let me set this back up. You would just combine these. We basically already did that, right? That's the 23 24ths. Then I subtract that. And what's a whole x minus 23 24ths x? A whole x minus 23 24ths x. So if you cut it up into 24 parts and you take 23 of them away, how much of x is left? 1/24. So you get exactly where I got to. Okay, okay, cool. And there could be other ways to do this that I just didn't even think about. There almost always is. Yeah, I want to be a little more specific, like on number 16. I think on the quiz there was a problem where you had to figure out the best method to use. So I'm going to be a little more specific. Like I have the same exact problem, number 16, just I wanted you to do 2 different ways. Okay, I'll lock it. Yeah.
Maybe 3.
3? The one about 5/x? Okay. So let me ask you, what method do we have? So I promise you I'm getting to that question. If I said, which one of these is bigger? What do you got, Jeff? Sure. What's the shortcut to figure out which one of those is bigger? Yeah. And again, we're using cross multiplication to explore a problem. We're not using it to solve something. There's only one place you can use cross multiplication directly to solve something. That's if you have a fraction equals a fraction. Cross multiplication is solve it, right? Here is sort of a tool we're using. So 267 times 4 is something 1,040, 1,068.
1,060.
And then 11 times 90. Right? So then, whichever way, as long as you take that up here and that up there, whichever way you would put this here is the way you would put it there. Now, what does that have to do with the problem that you asked me about, right? You're being very patient. All that shit's nice, Jeff. So the problem I actually gave you was if, wait, is that what? Yeah, if 5 over x is less than 9 over y, then is 9x minus 5y positive? Do you see how, real quick, this is greater than that? Is this times this minus this times this positive? Yeah. I don't know if you guys see what I'm saying. So I'm kind of taking this one extra step. So what's the immediate thing I could do right now based on what we did up here? Right? So 5y, keep going. 5y is, you're equally dead, less than 9x. So that I know for sure. Right, because I think I say, don't I say? No, but we're assuming right now we only have positive numbers. So x and y are both positive. I want to explore this number, right? How do I make that show up here? What do I do to both sides? I want 9x minus 5y to show up, so I know something about it. How do I make 9x minus 5y show up? What do I do to both sides? Minus 5y. So I get 0 is less than 9x minus 5y. If 0 is less than that, what kind of number is this? Yeah, and what do we call that? Positive. Okay, cool. Do you guys see that? So again, this is the part students, I don't care what level you're at, this is the part students kind of hate. The higher the level you get, the more problems you get that are not exactly like a homework problem, right? It's exploring an idea. So this idea can be used in this kind of problem. And there's some hints in the problem that tell you which way to go. 9x, well, how do I make 9x? I multiply that x up. Oh, I do the shit we could do up here, and then I kind of try to make that show up. So there are kind of hints in the problem that tell you which direction to go. This is not like some standard, well, this is how you do it. This is just some shit that I'm like, oh, because this is true, I can do stuff like this. That's the hardest thing for students to get, right? And that's, as a math teacher, you don't know how many times I've had students say, your test was nothing like the homework, oh my God. Especially the higher the math class is. And I don't know, have you guys, I'm sure some of you guys might have said the same thing to your teachers, but what I try to tell my students is the concept is what's important, right? I'm not gonna give you the homework problems with numbers changed. That does nothing to tell me if you understand the concepts. All right, I'll stop. What about number 4 right there? Hopefully we've done enough of these maybe. What kind of strategy would we use on number 4? It's a strategy, but it's built off of a property. What do you guys notice about number 4? Is there something that jumps out at you about number 4?
The addition equals 1.
The addition of 5/8 and 3/8. I would like it, but and I know you don't mean this, but of course you can't do addition first. What's the other part though in the problem? They're both the same, right? So then what property could I use, kind of like in reverse? Don't both terms have a 9/13? Both terms have a 9/13, which means they must have been given a 9/13. It must have distributed a 9/13. So I can undistribute a 9/13. The way I look at it is I don't even do that shit. So let me show you. I really want this to make sense. If you don't like what I just said, well, that sucks. But what was it again? 9/13 times 5/8 plus 3/8 times 9/13. Let me see if you, here's the way I look at this. This is 5/8 of something plus 3/8 of the same thing. So how much of that thing do I have? If you have 5/8 of something and you add 3/8 of that thing, how much of it do you have? One of it. I have 9/13. Now what's the actual computation behind that? I can take a 9/13 out, and there must have been a 5/8 plus 3/8. That's 1, like Brooke said. 1 times that is that. Something that happens pretty often in math is something like this. You'll get like 8 minus 16 thirds, right? So here's a quick way to think of this. This is 1/8. That's amazing what I just said. This is 1/8, which is 3/3 of an 8, minus 2/3 of an 8 is 1/3 of an 8. Done. That's a whole 8. That's 3/3 of an 8, minus 2/3 of an 8 is 1/3 of an 8. Done. Yes?
How did you add 8 on the side?
Oh, 16 is 2 times 8.
Oh, okay.
Yeah. So this is 3/3 of an 8, 2/3 of an 8. So it's very similar to this. This is 5/8 of this plus 3/8 of this is a whole one of those. You don't even have to do the distributive step. If you don't like what I just said, you can just do the distributive step. That part comes back out, and then this you can just add together. Is everybody cool with this step here, this to this? Because if I distribute, I sure enough get both of these, right? Okay. Yeah.
So it simplified would be 9/13.
That's it? Yeah, 9/13. So listen, if I had 1/8 of a tank, all right, let me do the same. If I had 5/8 of a tank and I put 3/8 of a tank in, how much of a tank do I have? I have 1 full tank. Yes, I have 1 tank. You with me? So that's exactly what it is. If I have 5/8 of this and I add 3/8 of the same thing, I get 1 full one of those. That's all that's saying. Okay, good. I got a couple of these. As a teacher, it's sort of like, like a comedian wants to see people laughing. A teacher wants to see people going, oh, or, oh, yeah. And not this. That's bad. Especially a whole classroom full of this. I'm like, oh shit, okay. By the way, feel free to make that. I'm not making fun of you, because sometimes you have to make that face, but follow it up with a question. That's the most useful thing. Anything else? Y'all cool with scientific notation stuff? Normally that's pretty straightforward. You sort of remember doing it before. It's normally pretty straightforward, yeah.
Number 2.
Oh, okay. So let me ask you a general question. If I'm given this is sort of like a homework question. If I'm given 2 numbers, the GCF, should that be bigger than the numbers or smaller than the numbers normally? Yeah, because what's the F in GCF? Factor. So factors of a number are always going to be smaller. There's one time that GCF is not smaller than the numbers, and that's if the numbers are either the same number, well, actually that's it, the same number, right? So if I said, what's the GCF of 8 and 8? Well, it's freaking 8. Well, what's the GCF of 4 and 8? 4. Smaller than 8. Are you kind of with me? So GCF always is smaller, almost always, right? But it's kind of silly for me to go, what's the GCF of 10 and 10? What kind of question is that? LCM, M of course meaning multiple, LCM is almost always going to be bigger. And again, the one time it isn't is if they're both the same number. The LCM of 8 and 8 is 8. So, when I have, writing the DNA of a number, writing the prime factorization of a number leads to a lot of shortcuts for things. And in this case, it's like a pure direct shortcut. What are the numbers again? Where do they go? There we go. By the way, whenever I teach this class, it feels so weird to write the time symbols, but oh well. I don't know if anybody in here feels the same way. All right. So GCF, what's the C stand for? Common. So what number would not show up in the GCF that's in one of these numbers? 17, because would you say 17 is common? Okay, so do you see what I'm saying? Already we know 17 is not going to be part of the GCF because it's not a common factor. So the shortcut we eventually get to is, it comes from this. This guy's got 4 3s, but this guy over there's only got, so how many 3s do they have in common? 2. So this, you guys remember the shortcut for this. To build up the GCF, I just take the smallest power I see on each thing, right? Is that all right? So then I would take the square and the 3. What about the 5? 5 to the 5th. What about the 11? Second power. What about the 17? The 0 power, right? Because this guy's got no 7. So whatever the hell that number is, it is the GCF of those. I like it. LCM, and this idea of shortcuts is too freaking beautiful because LCM is just the opposite. It says, I'm going to take the biggest freaking, right? Biggest freaking power from both. So what's the biggest power between the 3? I mean, now, do you understand why that works? This is more important than the actual just doing the shortcut. Why does the shortcut work? Because whatever I write here, I have to find both of these numbers in it. And nothing more, right? So whatever I write here, I've got to be able to find 4 3s in it and 2 3s in it. So if I write 3 to the 4th, I found both. That eventually translates into the shortcut. Just take the highest power on each number present in either of those 2 things. So I'm going to take all 4 3s. I'm going to take 6 5, 5 11s. I'm going to take 1 17 because that's the highest power I see on 17. And then of course whatever the hell that is. But I mean, if I ask you this kind of question, you can just leave the answer like this because the problem gave it to you like that. You can leave it in that form. If you want to multiply it out, you can. Is that better? There was some confusion between the 2. Just remember, I don't know if it's because the word greatest makes you think big, so you think the answer is supposed to be big, but it's the biggest common factor. The answer is going to be the biggest number that they both have in them. So at most, it could equal one of the numbers. It's the biggest it could be is to equal one of the numbers. LCM, M is multiple, multiples 3, 6, 9, 10, 20, 30. That gets bigger and bigger and bigger, right? Okay. Is there anything we haven't talked about on the practice? What about, like number 7? Is number 7 a decently? I made number 7 pretty nice, actually. What do you have to do on number 7? Yeah, make the outer ones the same as the inner one. And then, of course, what I'm looking for, I don't know if I've really, this has been stated, but why is 1.1 over 12, why is that not a fraction? Yeah, so you have to have whole number elements where the bottom's not 0, correct? So inherently in this problem, I know my answers are going to be whole numbers. right? They have to be valid numerators for that middle number. So once I build those up, I can see which numbers fit in between. Done, right? Is that cool? What was the shortcut to finding a fraction between two given fractions?
Add straight across.
Yeah, so if I give you 4/9 and 11, what do you got, Jeff? 14ths? Sure. And I want to find a fraction between those two. The quickest way to answer the question is just add across. And again, I showed you why that's true, right? So it would be 15/23. You should be very concerned. I've already made a big deal out of this, right? This problem is not add these, because that's definitely not what we would do. This is a process that finds a fraction between two given. And I already told you, if you're going to show this to students, you got to be really careful, because then they'll just start adding stuff straight across for everything. If I want to find a fraction that is exactly in the middle of these two, that process is much worse, right? Because what do I have to do that?
Change them to common denominator.
Yeah, I have to add them and then
Over two.
divide by 2. Right? You guys remember that? So if I just ask for a fraction that's between these two, dear God, don't find the one that's right in the middle. Just add the damn things, right? Now, if you find the one that's in the middle, that's an answer. But that's way more work than you had to do. Okay. By the way, what would the LCD be here? Why is it really quick? Are these relatively prime? 9 is 2 3s, 14 is 2 and 7. Do they have anything in common? No, so they both need each other. Right? I multiply this by 14, multiply this by 9, so relatively that's not as bad of a problem as it could be. You want the bottoms to be relatively prime, because that's the one time you can just multiply them together and get LCD. Okay, I like it. By the way, just to throw this out there, if you feel ready for the test, you don't have to stay. But what's funny is I get to a point where I have a bunch of people staying, they're all like, just want to be here in case somebody asks a question. Ask a question. Okay. I think we're, except for number 14, I think did we talk about 16? Yeah, 14 and 16 we didn't talk about. Are those both okay? I mean, what do you do with 14?
Line decimals.
No, you don't have to line up the decimals. In fact, you can immediately get rid of them. What does range estimate mean? Yeah, you round them all down. So make them a nice whole number and then round them all up. And that's your range estimate, right? So that's really useful if you don't have to be as precise. And then 16, I think I did say something about this very quickly, but can you do both of those, A and B on number 16? I guess so. So when I say use distribution, that could be confusing because there's a few different ways to do it, but I would hope it's kind of obvious. Which number do I want to break up? 4 and 0.5, right? So if I rewrite this as this, it's very easy to do 4 times 60 and a half is 16. Do you see that? That's the whole purpose of using distributivity to help. So 60 times 4 is 240. Half of 60 is 30. So I get 270. If I want to use good old compensation. By the way, I think compensation has come up more often than some of the other stuff because it's one of my favorite ones. I think it's the most useful one. But how the shit do you do it here? So normally compensation is trying to make one part of the problem look much better, right? So obviously I think you would agree, nothing against it, but the 4.5 is the worst part of the problem. What's the lowest number I need to multiply by to make that a nice whole number? 2. It's fundamentally half of something, correct? So if I multiply by 2, so where do I get that factor of 2? I can't just make it 60 times 9. That's a totally different problem. So of course I'm going to steal that factor of 2 from the only other thing I have there, 60, right? So if I write 60 as 30 times 2, so all I've done is rewrite 60. So this is why it's called compensation. One thing, the boss, the 60, gives 2 of itself to the employee or whatever, right? Good old capitalism. Sorry. Someday we'll get past it. So 30 times 9, which thank God is the answer we got before. So they're both the same problem. You better came up with the same answer, right? And that, believe it or not, this is a really simple one to see that they have to be the same answer, but there's multiple places in mathematics where students like, well, why would I get the same answer? We did a totally different, well, it's because it started off as the same problem. So it has to be the same answer no matter which way we go. Of course, number 13, should be able to knock that out pretty well. Yeah, I think that's all of everything on there. Oh, is that why you're asking number 8? About the LCD and all that kind of stuff? Right? Yeah. So let me go ahead, I'll give you guys the answer key. Remember the Mr. Last Name one? I love this. The best thing in the world for teachers to make a mistake on their own answer key, but I'm still averaging about a 97. So number 10, instead of 24, I decided to put a 4 there. Sure. So real quick, number 10. Good job, Jeff. You almost got there. So it should be 18,000 equals 1/24th x, and then you get whatever the number was we got earlier. Okay. I think I did okay otherwise. The one thing to be careful about on number 13 is the one place you should use the word and is where? Because, decimal point. So we say stuff like 427 people are coming to the whatever, but technically the word and should denote where the decimal place goes. In fact, if you've ever filled out a check, you know exactly what the hell I'm talking about. 437 and 10 hundredths dollars or whatever, right? It's been a long time since I filled a check out, though. But, Aheen, how did I end up with that?
I gave it back to you. I have one in my car.
Oh, I see. That's right. Okay. All right. Anything else? I am very fine with having an early day, but I want to make sure everybody's got their questions answered. Like I said earlier, don't sit there looking at me. You can leave if you're ready. If you're not ready, just let me know what it is you need help with. Otherwise, I'll see you on Thursday. And then we got Thanksgiving.